All right, let's do, what did I say? Shifting and XOR. All right. XOR. Okay. All right, give me a low number.
2.
All right, we'll do 1. Okay. 5 to 10.
7.
7. All right, great. So 7 in binary. What do we have? We have 1, and then we'll have the 3 and the 4, and then a bunch of zeros. All right, and there we go. And that's in base 2, guys. This is, of course, base 10. Everyone understand this notation? Base 10, base 2. 1 plus 2 is 3, plus 4 is 7. Everyone used to this notation? No. Oh, everyone. Oh, is everyone used to base 2? Whoops, I forgot to ask that. No. All right. 2 to the 0, to the 1, to the 2, to the 3, to the 4, to the 5, to the 6, to the 7. And 1 means you add it, 0 means you don't. What's 2 to the 0? 1. Yeah, you did. It was a pretty bad one, too. You lost. What's 2 to the first? Hold on. You got this. You got this.
What?
I'm like, I don't know. You made him sit down.
What's 2 to the 1?
1, 2.
All right, great. What's 2 to the 2? You don't have to answer that one. We'll let someone else take it, okay? What's 2 raised to 2?
4.
4. Thank you. So 1 plus 2 plus 4 is. What's going on in life?
That is a good question.
Well, if you're trying to get 7, do you add 8? No, because 8's greater, 16's greater, 32's greater, 64 is greater, 128 is greater, so you don't activate those zeros.
So you
Let's get why you have zeros.
Yeah, we learned this not working.
Why do we have those zeros?
Because
You're storing things in fixed size. So right now we're storing everything in how many bits?
0.
8. I like 7. That was a good one, but no, it's 8. Which is a byte. All right, so we're doing 1 byte numbers. Okay, now, if we're going to take 7 and we're going to upshift it by 2, that's the notation. You take 7, you upshift it by 2. You're going to take all these numbers, move them up 2 spaces, and put zeros over here. So, this is really equal to, here are 5 zeros, 1, 2, 3, and then you upshift it by 2, which means it's equal to 0, 2, 3, 1, 2, 3, and then 2 more. You see what just happened?
Yeah.
Everyone good with this? All right. What's this? Well, I forgot to do it myself.
I don't have a piece of paper.
28?
Oh,
It should be 28. Okay, hold on. So this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. So it's equal to 2 to the fourth, which is 16, plus 2 to the third, which is 8, plus 2 to the second, which is 4,
See, I said that. But just couldn't do
which
it.
is 28. All right, guys.
Glare.
Clear?
Glare.
Glare! Oh!
Not that.
only a little bit.
The glare.
There. Now my.
There we go.
I'll just stand like this.
Magic.
All right, so it's 28. Does anyone see what we just did?
Yes.
So what is this doing?
It is upshifting.
Upshifting. All right.
Is there a particular relation between the number you're upshifting by and the how it affects?
Yes, there's a direct correlation. If this was a 3, the number would be 56. Yes. What this is really doing is 7 times 2 raised to the what's up there?
2. So 7.
Right, it was 4. If that was a 3, it'd be 2 raised to the third, which is 8. By the way, which of these do you think is easier for a computer to do? Shift or multiply?
Shift.
Shift, yeah, by a lot. But anyways, you'll get to that more in architecture.
Yay.
Thank you. Yeah.
Yeah.
Yeah. Okay. Now, all right. So they're shifting. Do you think you can downshift as well? What's that? No, that's not what XOR is. So if we did
That's disease.
7 downshifted by 2, you'd still have 5, 1, 2, 3, and you'd be downshifting by 2, which is just equal to wait, 1, 2, 3, 4, 5, 6, 7. I missed some. There we go. All right. Okay, everyone good? All right. Erasing that. Good old XOR. All right, give me some numbers that are less than 128.
127. I should have seen that coming. I should have seen that coming.
Why did I not see that coming? All right, give me another number.
125. 63.
Okay, under 100. There.
63.
63. I like 63.
One.
And which one?
87.
And 87. All right, that's the XOR.
Okay.
Didn't see that coming, did you? All right, what's 63 in binary?
Oh, jeez. Oh.
132.
Thanks, Captain Obvious. Who was that?
That was not
Oh, did I do that?
Someone once, basically.
Yeah, I think I got that right. Yeah. Because that would be 64, so you'd have to turn all the other ones on. All right, caret. Now we're going to do 87. So what's 87 minus 64? What's that, 23? Y'all just had to make this difficult. So not 32.
I said thank you. That was easy.
Whatever. 16, so after 16 you have 7 left. Okay, good. That makes it easy, because then it's 8, and then 1, 2, 3. Perfect. All right. So if we're going to XOR this, all right. XOR means exclusive OR. It means it's either one or the other, but not both and not neither.
Okay.
So it's either 63 or 87.
And you do them by bits. Oh, 1 XOR 1 is 0 because it's one or both, one or the other, but not both. Right now we have both. 1 XOR 1 is still 0. 1 XOR 1 is still 0. 1 XOR 0 is 1 because you only have one of them on. So it's 1 XOR 1. 1 XOR 0. 0 XOR 1. 0 XOR 0. All right. Who said 1? All right. Y'all see what what's that is doing? Okay. How does that help you? What's that?
No, that was going to be my question.
You'd be
Why
hard pressed
is
to get
it
it.
useful and whatever?
You'd be hard pressed to get it to equal out the same thing.
All right. So, what does this? Okay. When it comes to hashing, the point is to just kind of randomize numbers as much as you can, or equally distribute them out. Hopefully, you can see that XOR is kind of jumbling up the numbers a little. You might be adding some shifts because it's moving the bits around. But the idea is you want to kind of just randomize the numbers as much as you can, as quickly as you can. We're not going to go into too much more hashing because that is cryptography. But the point of this is to show that with certain operations, you can quickly randomize the numbers somewhat. For example, how hard do you think this is for a computer to do? Not that hard. Is multiplication harder or easier? Harder. Way harder. So XOR, actually XOR and shifting will take 1 or fewer clock cycles is what we're just leave it at that for now. Multiplication takes way more. So this is quick. Oh yeah, we were doing a little segue here. Any questions on XOR and shifting and why we're using it? Nope.
Yeah, why are we using it? Like, I might have forgotten, or I'm trying to figure that out in my head.
So we're trying to use these in order to take a key and jumble it up so it maps to some random location in the array.
Okay.
So
All right.
right now, if the keys was just one integer, you really can only mod it. But what if it's a string? Oh yeah, what if it's a string? What could we do? What's that?
Convert it to an integer.
Convert it to an integer, right? How would we convert a string to an integer? All right, so, all right, hold on. Y'all all spoke at once. It was amazing. But yeah, first off, each character has its own integer value. So now we have multiple integers. What could we do with those? We could add them together, sure, but you'd have multiple names that would add to the same thing, right? But you want to jumble it up some more, so maybe you would add some of them, shift them around a bit, XOR them around. Maybe you just XOR each digit. Maybe you'd put two of them together, so you'd have a 16-bit number, and then XOR the next two 16 together. You know, there's different things you can do. So for example, let's do a, you know, that's great. Let's write an example so this makes some sense. All right, give me a 4-letter name.
Paul.
Had to say this. I'm going to make it all caps, so this will help me out. All right, so each of these are digits, right? And we want to map this to an integer. All right, what's the value for P?
Is it 20? Is A start at 20?
No, capital A starts at 65. I don't remember. Come on. Look, just go to the table, guys. Someone type ASCII character chart. We'll make this happen. I don't have a GUI. I mean a web browser.
Got it. Come on, a room full of computer science majors and we can't get this.
Okay, so what's capital P? 80. Thank you. All right, so this one's 80. What's A?
65.
65. I knew that. What's U?
85.
85. And what's L?
76.
76. So one thing we could do is we could just add them all up. Ooh, let me put that on the board. There we go. We could add them all up. What would that equal? We're terrible at math, aren't we? Or arithmetic. What's that?
6. Last number is a 6.
Last number is a 6. Okay, last number is a 6.
306.
Whoa.
306.
306? All right, I'm just trusting y'all. All right. Now,
You should never do that.
if you had a ton of names, how many would probably map to 306? There were 4 letters. A lot. Even some 3 letters. Well, 3 letters probably won't, but yeah, there'd be a lot to map.
Maybe like 4 letters. Like
Yeah.
A, B, C.
Right. There might be a lot here. Okay. So what could we do instead? Well, we could take 80 and we could upshift it by 8. So what's the binary representation of 80? So 64, what would be left over? 26?
6
So not, so then that's 16, so then that would be
zeros. So there's nothing there. Yeah. It's 80 minus 64 is 60.
Yes.
So you were right, just there was nothing after that.
good. There we go. There was a glare. 64, 32, and then 1, 2, 3, 4, and then what's 65? Okay, this one's gonna be easy. 0, 1, 2, that's 4, 1, 2, 3, 1. Okay, great. And then 85, let's just borrow this guy. 0, 1, 0, 1, and then we need to put a 5, which is going to be those two right there. So 0, 1, 0, 1. And then 76, oh man. 0, 1, and then what we have left over? That would be 12, right?
1.
Yeah, so 0, 0, and then you have 8 and 4 to make 12, and then we just need 2 more zeros. Okay? So that's how they're stored in the computer. Now, if we wanted to make this a 16-bit digit and make this a 16-bit digit, how can we do this? You would upshift this by 8, which would add 8 zeros to it, and then you could add this guy. So by doing upshift here, and then you add this guy up here, you would get 0, 1, 0, 1, 1, 2, 3, 4, 0, 1, 0, 0, 0, 2, 3, 1. And now you'd have a 16-bit number from these two guys, right? You could do the same thing here. Again, upshift and then add, and I'm going to write that down here, so you'd have 0, 1, 0, 1, 0, 1, wait, I messed up, didn't I? 0, 1, 0, 0, 1, there we go, 0, 1, 0, 1, 0, 1, great. Whew. And then you could just XOR them, and you'll probably get something a little more random than what you get from up here. Also, you get a number that's probably bigger than 306, so hopefully it'll be a little more even distribution.
But so that doesn't guarantee that they will only be like duplicates.
No, there's no guarantee. That's the thing about hash table. It will never guarantee that there's no collisions.
So if you use an official hash table in a language, there's a chance that you map of two names, and only one of them will actually end up there.
Remember, we're using a linked list. We're doing a hash table chaining, so you have two that go to the same spot, but that means two entries in the linked list.
Wait, but okay, so if the entry is in a linked list, that means, wait, hold on a second. But the array we have, the size of it isn't like the size of all keys, right?
No, it's usually smaller.
So it's
way
the linked
smaller.
list of which has the key and the value, right?
I'm sorry, say that again?
So the linked list has a key and a value.
Yes,
right?
correct. It
Like-
stores both the key and the value.
So the keys into the nodes, the keys would be the same, right?
I see what you're saying. That's different. So if you have the same name, you usually overwrite. If you have the same key, sorry, you usually overwrite the old one.
So that's what I was talking about.
Oh, okay,
If
then
you
yes.
find if you're lucky enough or unlucky enough to find two names which would, according to the algorithm of the hashing, overwrite each other.
Oh, no. The hash algorithm just tells you which entry into the area sorry. Let me start over. The hash function tells you which
In the array.
element you jump to in the array. And then you have to search the linked list afterwards. So the key is still going to be unique because you have to search the linked list. This function is just trying to trim off as much as possible by just jumping to the correct location in the array.
Okay, this makes more sense.
All right, so you see how this is kind of jumbling up? Again, why does this jumble it up? It just does. That's actually the official reason. Yeah.